Now, to help bring us through this, the next speaker is an Underwood Distinguished Professor in the School of Integrated Technology, Yonsei University. He's now an Editor-in-Chief of the IEEE Transactions on Molecular, Biological, and Multi-Scale Communications. He has served as an editor for the IEEE Communications Magazine, the IEEE Transactions on Wireless Communications, the IEEE Transactions on Molecular, Biological, and Multi-Scale Com, the IEEE Wireless Communications Letters, the IEEE Transactions on Smart Grid, the IEEE Consort Technology News, and the IEEE KICS Journal of Communications and Networks. Ladies and gentlemen, let us welcome Professor Chan-Byoung Chae.
Hello everyone. Can you hear me well? Hello everyone. Can you hear me well? I have any technical problem?
Yes, Professor, we can hear you loud and clear.
All right, thanks so much. Thanks for the introduction and also thanks for the invitation. This is Chan-Byoung Chae from the Yonsei University. So it's my great pleasure, indeed an honor to have this opportunity to introduce our some research progress and a new communication paradigm. So for this topic, I have some wonderful colleagues, and I'd like to thank my students, Bon Hong and Changmin first. So I've checked the program of this workshop, and you have the really wonderful speakers. So I believe you have heard about the 6G wireless technology so many times. So in my talk, I'd like to introduce some new communication technologies, new story for the future networks. So as you can see from the title, so we have two very well-known researchers, Einstein and Reynolds. So some people, maybe you might wonder how Einstein and Reynolds contributed communications. To have the answers, let's start a journey. Oops. All right. Before starting my talk, let me take the quite short introduction to myself. Again, this is Chan-Byoung Chae, and I am a professor at Yonsei University. Before joining the Yonsei University, I was with the Bell Labs in New Jersey for almost 2 years. Before that, I was with Harvard University in applied mathematics, so working on some more mathematical problems. So I'm now an editor-in-chief of the IEEE Transactions, and also I am a distinguished lecturer. So if you have any other chance, I can give the some more talks on different topics. So here is the outline of my talk today. So I was told I'm given about 45 minutes for the main part and the 15 minutes for the Q&A. So I will try to deliver the key messages with not really many math equations. So my talk consists of the main three parts: the fundamentals of molecular communications, and also the communication theory for the molecular communications. And finally, so we will have some test bed and prototype results to validate our some new novel concepts. So, you know, in the first parts, I will start with quite famous researchers like Einstein and Brown and many others. In the second part, so we're going to cover like channel models and modulation techniques and detection algorithms. And we will also see the prototype results. You know, this is a new communication paradigm. So believing, you know, seeing is believing. So we need more like a prototype to believe this concept is feasible in practice, right? All right, let's move on to the some fundamentals. Our research area has gone through a series of the revolutions with the introduction of new communication media, sometimes from wires to air, and most recently, even to liquid-based media. So the introduction of such different communication paradigms has catalyzed the development of the novel applications that were previously unthinkable. So most recent of this paradigm is molecular communication, which facilitates healthcare applications involving intra-body networking. So by providing a means of communication through the ubiquitously connected blood vessels, like artery, vein, and capillaries, the molecular communication-based e-health applications, and it enables a lot of the new Internet of bio nano things services. So I just want to ask you a question here, very simple question. Is there anyone who could differentiate 6G from the 5G? Even 5G, it is now being well deployed, right? Even in Singapore. But I believe there are somewhat limited killer applications for 5G. In 6G, maybe beyond 6G, B6G. So we're going to have a quite different applications. That's why I here claim biological, the layer on top of well-sized 7 layers to support the e-health applications. So sometimes we call the RF technology, radio frequency part, is layer 0. So here we add one more possible approach, layer 0, instead of having the RF technologies for the other applications. So to realize the IOBNT in practice, here we have conceptual some figure. So the health monitoring scenario that we spotlight here employs the nanomachines that can communicate with each other via molecules, so that the system can have a better biocompatibility than a system employing the electromagnetic component. So the machines are capable of adaptively transmitting and receiving target molecules in any application in vessel environment with the help of the state-of-the-art nanomachine technologies. So for this application, we should first understand the fundamentals of molecular communications. And I will get back to this slide after the introducing some technical details. So then, what is nanocommunication networks? It interconnects the several nanoscale machines to carry out sometimes complex tasks or sometimes simple tasks in a cooperative manner. So there are 2 types of nanonetworks, electromagnetic based and molecular based. So for the molecular communications, a nanomachine sends, receives information encoded molecules, as you can see from this figure. So suppose we have, okay, so we can easily design the system like this. Suppose we have a controllable spray. If I spray perfume, just for example, and you can easily smell it, and you can decode this smell into like a binary 1. But after some time, which indeed is related to the symbol period, if you don't smell anything, you smell nothing, you may think, oh, I sent jitter. So this is a very simple demodulation and demodulations for the molecular communications. So we here compare the differences between the traditional electromagnetic communications and the proposed molecular communications. So obviously we have the totally different carriers. We do not have the electromagnetic wave for the molecular communication. And due to the nature of the chemical diffusion, the propagation speed is extremely slow. The thing is that here, we're not arguing we should replace 5G millimeter wave networks with the molecular communications. We have the quite different applications, and we believe this approach is quite useful for some other applications in 6G era or in the B6G era. So we have the totally different applications, and we have different resources, and included information is also quite different. So I know it's hard to believe this concept. Theoretically, it's possible, but what about in practice? To answer this question, I prepared a very short video clip. So let's watch first. So here, we want to transmit 6 alphabets, Yonsei, the name of our university. But in this system, we don't have any RF port. We do not have antenna. We do have only like a fan and also some messenger, the molecules, and simple gas detector at the receiver side. And you can hear some sound, right? That's the when we release a certain amount of the messenger molecules, and it delivers certain message. And finally, so we successfully received the 6 alphabets. So what did you get from this video, and what do you think of this test bed? You know, this is the first communication test bed without any RF technologies. So surprisingly, we were able to deliver some alphabets, right? Like Yonsei. So here we have the also other some different test bed with more advanced techniques, and you guys will see them during my talk later. All right, you may wonder where we could use this approach. So we here have these 3 representative applications. For free space environments, we could have the tactical, the macro scale, or nanorobots that have the robustness again against the eavesdrop. So for in-visit applications, it's already introduced host monitoring and nanorobots and or target drug delivery system could be some good examples. For underwater applications, and we have some target systems, and also the leakage detection for oil pipe may be quite useful. But I will mainly focus on the first and second applications for my talk today. So let's talk about the diffusion-based dynamics, very fundamental stuff. The Brownian motion. I believe you have heard about the Brownian motion quite several times. This is the random motion of the particles suspended in a medium, like in a liquid or a gas. So this motion, as you know, is named after the botanist Robert Brown, who first described the phenomenon in 1827, while looking through the microscope at pollen of the plants, Clarkia porchella. I'm not quite sure my pronunciation is correct for these plants, but that is the one he observed these phenomena. So in 1905, almost 80 years later, the physicist, Albert Einstein, he published a paper where he modeled the motion of the pollutant particles as being moved by the individual, the water, the molecules. So making one of his major scientific contribution. This topic was this PhD dissertation. In his PhD dissertation, he never talked about relativities or never talk about other quite relevant topics. It was about the molecules dynamics. So this, Einstein's explanation of the Brownian motion, it served as convincing evidence that atoms and molecules exist, and also they further verified the experimentally by here the third well-known the scientist Chan-Byoung Chae in 1908. Oh, by the way, he was also awarded Nobel Prize in Physics in 1926 for his work on the discontinuous structure of matter. So the Brownian motion, I told you, the random motion of particles, and I believe we all learned about this Brownian motion in engineering mathematics class during our undergrad studies. So the final equation here, this equation is the first order in time and the second order in space. So we know the solution of the diffusion equation is Gaussian distribution, but this is true only for when we care about the distance. When we care about the time, like what we have in the communications, things are different. So let's take a simple example here. Suppose we release a certain amount of messenger, the molecules at x0 and t0. If you assume, if we are interested in the location of the diffuse the molecules, then we'll have the Gaussian distribution. However, if we are interested in the time, and we have inverse Gaussian distribution, right? So I will skip the some details here, and all right. So one of the simplest stochastic system here. This is a Brownian particle, and given the Brownian motion is used as a tool to understand more complex phenomena, it is important to understand the probability of the first passage time of the Brownian particle of the reaching some position and also some different location from its start position. So this is done through the following equations, and then okay, here I just want to skip some part to deliver more key messages, but the thing is that first passage time density here, this is a quite important probability a particle has first reached the point that is a receiver at exactly the time some index, right? So we have the inverse Gaussian distributions for the 1D space for just simplicity. But the equation is quite different from what we had for the electromagnetic systems. So here we have the reviewed quite key parts of the some diffusion mechanism. Was very essential to understand the channel of the molecular communication system. So from now on, let's focus on communication part. So, the goal of communication system is to transfer or deliver some information across space and time. So to achieve this, the signal needs to be generated by transmitter in accordance to the information that is intended to be transferred to receiver. So this signal then propagates to a receiver where the intended information is decoded from the received signal. Therefore, any communication system can be broken into major three parts, transmitter and receiver and channel. So here we show the block diagram, the representation of those three modules and their sub-modules. So basically, even for the molecular communications, so we have the quite similar approach. So we design the modulation, and we design kind of the channel coding, but we rely on totally different channel environment. We do not have any relay fading or spatial channel model being used by 3GPP people. Instead, we have diffusive channel and also some drift velocity, as for example, especially for imbecile networks. All right, so let's talk about modulation technique. So in the electronics and telecommunications, the modulation is the process of developing one or more properties of the periodic waveform called carrier signal with a separate signal that typically contains the information to be transmitted. So term analog, digital, the modulation can be used when the modulation signal is analog or digital, respectively. But so naturally, this question comes to mind: what resources can you use for the modulations for molecular communications? So to distinguish different symbols, and we can use concentration, time, space, and like a molecular type. Like unlocking in optical communications, we could have the different information just by controlling the number of the released the messenger molecules. We call this the concentration-based modulation. Similarly, the timing of the release can also be used, and spatial position of release is also possible. Above all, to have the high order the modulation, we could have the different types of messenger molecules. So here, very simple one that I explained before for our very first test bed. So concentration shift keying. The concept is quite simple and straightforward. So concentration of the sent received messenger molecules is used as the amplitude of the signal in and these parts. We can have square waveform. We can have the pulse like the information. We can have the multiple levels as well to achieve the high order the modulations. And for the timing based technique, the information is represented by various time, different time location, and simply this modulation encodes information on the time of release of the messenger molecules. But it also has some quite many drawbacks, and the main drawback of this approach is to have perfect synchronization across all the nanomachines, which is not really feasible in practice these days. However, theoretically achieve almost the best performance. And to have the more reliable transmission with the higher data rate, we also proposed isomer-based molecular type, the molecular shift keying. And just to introduce the concept, we used glucose with the 16 different levels, just by considering L type, D type, and also just by utilizing the properties of the isomers. But obviously, the complexity will be an issue, and receivers should have the multiple and different types of the ligand receptors to distinguish the multiple, the messenger, the molecules. But pretty much the quite nice idea. All right, okay, in the previous part, we have learned about division-based dynamics and communication units, a little bit of the channel modulations. So here, I'd like to talk about detection algorithms. So if time is allowed, I will also introduce the channel coding part. So, the detection, the most important part for communications. So similar to the RF communications, we have the simple equation here consisting of the channel parameters H, noise N, and the transmit a signal symbol X. And we just need to solve Y equals HX plus N, which is quite similar, right? So as the goal of the detector part is to minimize the distance here between X and the some decoded message Y hat. So we could rely on maximum likelihood and maximum R posteriori detectors. However, unlike RF communications, since the coherence time is almost zero due to the nature of the random walk, the diffusion mechanism, so most prior work on detection algorithm is based on the long-term channel characteristics. So, the extremely low data rates is one of the serious problems or technical challenges of the molecular communications. And we would like to send the more data with less errors, ideally no errors. So reducing the symbol interval is one option, but we need more sophisticated algorithm. That's why we mentioned here the MIMO stuff. And the biggest headache for the molecular communication is as you could easily imagine, the intersymbol interference. And as you could also observe from those figures, even if we release impulse-shaped molecules, there is long tail here, long tail part and long tail part. So with relatively short symbol interval, there is very severe the intersymbol the interference like that. We have quite a huge overlapped region only for the two conjunctive transmission. So to avoid this, so we could wait a long, really long time, but this is not what we wanna for the communications, right? So now let's talk about some more advanced techniques to resolve the problems that I introduced. So, the molecular communication is a novel and new paradigm that does not have any the RF components like RF antennas or RF issues, right? However, the molecular communication is also a communication engineering. It also has their similar communication problems. So in the last decade, since 2010 or so, to improve the link reliability and the system throughput, so we have the extensively studied topics like multiple input, multiple output, which is MIMO, and also full duplex communications and the relay networks. So recently I prepared some materials for these three topics as well, but I don't think I could introduce every details due to the time limits. So I will share the more slide if you ask the any questions after my presentation. So, I introduced, before I introduced the macro scale tabletop test bed. Remember that. So is there anyone who could guess the transmission rate for that test bed? So we sent 6 alphabet YON, SEI with the quite cheap fan and spray and chemical sensor. It cost only $50 to implement everything. So that it was the data rate. It was approximately 1 bit per second, which is way lower than our communications. In 5G, using FR2, the millimeter wave spectrum, we could achieve 3 gigabit per second order. With FR1, with 3.5 gigahertz as a spectrum, and we typically achieve like 300 megabit per second on average or so. So I'm not joking here. It's 1 bit per second, but I think you know, to transmit 6 alphabets, and at the time we used about 30 bits, which means it took about 30 seconds to deliver only 6 alphabets. Eventually, the main challenge is expected to be the technology with the higher data rates and lower error rates, right? So that's why we designed the MIMO system. And also, we assumed only one-way communications because suppose we are having some nanomachines in our vessel, inside of our vessel. We have some blood flow as well. It's quite different scenarios than what we have for RF communications. So we design the mono configuration. We design full duplex radios for molecular communications. And also we design the relay network to have the more reliable long range communications. So the second video clip. So, as we discussed, the spatial domain can be also obtained by like applying the MIMO configurations. And also one might argue that MIMO may not work in the diffusive channel because of the totally different channel characteristics. But we propose novel detection algorithms for the molecular communications with a 2x2 MIMO configuration, and we implemented the prototype to test the results. So let's watch the second video. higher data rate, 1.7 times higher than the size of communications, and we successfully received the YONSER. That was the molecular MIMO configurations. So, you know, the MIMO can also be used for the other purposes. So I will skip this slide, but we can use the free-space channel. We can use this concept for the vessel bounded channel and also for the water the communications. So, okay, here. So far, we have studied the fundamentals of molecular communications, but we need more practical systems so that we believe this new paradigm works. So before concluding my talk, I want to show you the practical system and that we implemented. So here, nanoscale, the molecular communications. I mentioned several times, we could use the molecular communications for health monitoring or target drug delivery the system. So we need real nanoscale robots for communications. So to realize the nanoscale, the concept, so we fabricated the human implantable nano devices for here, the basically the data transmission. So this is the system that we implemented while the entire communication model still requires like some enhancement to be used in practice. But the remarkable point of this work is that the nanoscale sensor we designed is specialized for the molecular communication task. The sensor is small enough to be implanted near the human skin while not being harmful. And so it is suitable for being a molecular communication the receiver. So we achieved here the data rate of the 2 bit per second with a reliably low error rates. So we conclude with a positive message that the bottleneck is not the channel uncertainty, but the mechanical units, so that the nanomolecule system can achieve even better the performance in the future the works. So for the receiver part, we used glucose detector. We designed glucose detector based on the zinc oxide materials. Some alphabets, and then we successfully decoded through the tiny nano robots. And we also propose mesoscale the test beds. So here, most prior were employed channel-based test bed, like assume prescale air diffusive channel. But the thing is that we have to implement some really human implantable nano robots, like what it shows, and the channel should be like invisible environments. So we design some novel test bed as well. One is like our heart. So it is pumping. And second, these are our human vessel networks. And third one, as a receiver, of course, we should shrink a lot so that we can put this machine into our body. And also 4 is like the some decoding the mechanism, decoding modules. And using that one, like to increase the data rate, and just by considering the multipath environment, this multipath environment is different from the RF communications. And we have the prototype here, 2x2, Bessel, the MIMO. So this is the last one, I believe, I prepared for your understanding. So for these contributions, like the what I showed you before, we got the best demo award from the Infocom and also from the WCNC, the conference. So okay, let me conclude my talk. So what will happen after this research? It's gonna be our journey's end. No, I don't think so. It will be a new beginning. Once you have some fundamental IPRs and macro scale, nanoscale, mesoscale, the verifications. So we're gonna have the technologies that will change the world, and it will be quite crucial for 6G and beyond 6G networks. So thank you so much for your attention, and it's time to have the some questions from the audiences. Thank you so much.
Thank you so much, Professor Chan-Byoung Chae, for that very engaging presentation. And of course, we'll now move on to the Q&A, and we have some questions already from our audience, starting with this one. And the question is, what is the major use case of molecular communication in 6G? Why can't RF or optical frequency be used for this?
That's a really good question. Let's think about this way. In 5G, we have the quite well deployed networks but we still have the almost same experience, like watching YouTube or sending the email, checking emails or something like that. But to have the real impact with the 5G, Korea government, we push a lot to have this smart factory or something like that. All right. In the factory, we can use the 5G technologies, especially ultra low latency technologies. That is the one killer application of the 5G. But what about in 6G? What other applications can we have? As I mentioned before, I think the health issues, biomedical issues would be somewhat critical killer applications. But if we just keep the RF technologies to monitor the health condition of our body, and it is really difficult because that the radius of our blood vessel is like in the order of the micrometer or maximum millimeter. So we may need few hundred terahertz or even higher frequency spectrum to use the RF technologies, which is not really feasible to have the oscillator or crystal to generate that frequency. And also pass loss issue with one more big hurdle to have the RF technologies for health monitoring problems. Yeah, that's why we can use molecular communication, which is the biocompatible and which is not quite harmful. And we can suppose, okay, let me have the example. Let's assume we have 2 nanomachines up and down of our heart. And those 2 nanomachines communicate quite sporadically, like 1 bit per hour or so. And the receiver detects somewhat promise the sequence and 101010 something like that. But suddenly the receiver observes some abnormal signals like 1111010 or something like that. That nano receiver can forward that information through the relay networks, like what we proposed, and then that message is delivered to the skin of the body, and we can get some alert messages on the cell phone, the smartphone. Oh, the machine number certainly has some abnormal that behavior. So you might want to go see a doctor to check those parts or something like that. So that would be the applications for 6G or even beyond 6G. So as I mentioned before, we are not arguing we have to replace the RF-based technologies with that one. Rather, we proposed one more possible communication mechanism to have the more rich the experiences. So is that enough for that question?
I hope so. It's probably a lot of insightful perspectives over there, and I hope that I will answer the question from our audience. And the next question that we have is, how do you overcome the full duplex self-interference? How is it done?
Right. I'm not quite sure the audiences are mainly engineers or some graduate students in engineering, but the full duplex has been also studied in RF technologies since 2010 or so. And we also had our own prototype for that. So main thing is that we have to mitigate very strong self-interference cancellation. But self-interference cancellation level of that SRIC is much higher than that of the digital signal coming from the other part. So we have to do everything we can do, like the cancellation in the analog domain, digital domain, with the linear components or for non-linear components or something like that. So for the molecular communications, and we also design somewhat similar approaches, like a passive cancellations, which are special the transmitter design, and also we applied very straightforward digital domain cancellation. That's the time domain subtraction. And also we design a little bit different one, like a transmitter, the waveform design for molecular communications. So we published that work in the IEEE Transactions on Communications a while ago in 2020 or something like that. And I can also share that the paper with someone who asked this question. So in sum, we've designed molecular communication specific SIC algorithms, and we achieved almost a double capacity, double throughput against the half duplex molecular communications. That was quite a good question.
Thank you so much for explaining that. Now, we have another question that's coming up here in our lineup, and it says, as you explained, the molecular communication has quite a low data rate. What data rate do you expect with current technologies?
Mm-hmm. So that's why I prepared the several video clips, right? As I explained, for the very first testbed that we implemented almost 7 to 8 years ago, it was only 1 bit per second or something like that, which may not enough for communication, but which may enough for health monitoring. So with the state-of-the-art technologies that we design for this application, I think we could now have up to 10 bits per second or so. But of course, it depends on the distance. Unlike RF communication, the distance is quite critical because we rely on the diffusion mechanism. So for a certain reasonable distance between the transmitter receiver, and then we could achieve the 10 bits per second, which is more than enough for delivering the monitoring information. But okay, to have the more impactful the applications, I believe it's better to have the kilobit per second order or something like that. And I think that we could achieve those the performance maybe in 2 or 3 years. And you know, in the 6G or beyond 6G, it will start 2030 or something like that. And by then, I think we have the quite well ready technologies for some special applications.
Thank you so much for that insightful answer. We have another question here from the audience, and it says, when do you expect to have this concept in the standard? Is it like smart factory with 5G?
Right. You know, surprisingly, IEEE already started the standardization for this problem. I remember the name of this standard is IEEE 1905 or something like that. But they have quite a different one strategies. But it's gonna be considered by the 3GPP people maybe later in 10 years or something like that. But the thing is that we need more kind of the requirement for the applications. If the 6G is only designed for the focusing quite conventional and classical communication purposes, they may not need this molecular communication concept. But in the 6G or even beyond 6G, 7G, if they wanna broaden their scope of the communications, and I think they will also consider this kind of somewhat ridiculous the idea but it will be the reality pretty soon, I think.
Thank you so much. And I think we've got one last question here. I think this person was trying to find out maybe what's the inspiration behind some of your work. And he says, how did you come up with this novel idea? Would you be able to elaborate?
You're right. That was about that. This gonna be about my personal story. But you know, the before coming back to my home country in year 2011, and I was with the Bell Labs. Bell Lab is quite the famous for the wireless communications. At the time, I designed the massive MIMO system, and also I worked on the small cell networks. And in 2011, I spent some time think about, what I want to do as an professor in Korea. We also have quite a lot of the many faculty members working on the communication theory. So I try to distinguish and differentiate myself by performing somewhat new research problems. So in 2011, I tried two different researches. The first one was about the real prototyping. That's why we have in my group, we have the 5G networks and even 6G, very simple test bed as well, using sub-terahertz spectrum. We're using our own novel idea on reconfigurable intelligent surface, which is a passive one, which is quite different from the other folks. The second direction was about this one. I wanted to have something more impactful, something more new stuff. So I started to work in this topic just by reading some fundamental papers and textbooks in biology and chemical engineering to have the more this kind of impactful research. So I took a risk, and I didn't publish a lot of papers during that time. And finally, thanks to some my wonderful colleagues, and we designed really nice system, and it's now being considered, it's now being acknowledged by the other the professors and researchers. And we hope we have the more international collaborations to have the more impact. I hope it answered that question.
Thank you so much, Professor Chae, of course, for your presentation on biological layer for 6G and beyond 6G, and of course, for answering all those questions from our audience. Thank you so much for the participation. Thank you once again, Professor.
Thank you so much for your attention. Thank you.